So we're still in the finite difference method here. And we would like to put general format just to use the same language we use in CFD all the time, and go through our first example to see how we can actually apply the finite difference method in a very simple conduction problem. So we cover the forward or backward finite difference method, right? If you go back to the couple of slides or the previous recording, you will see that we covered that. So, for example, when we did for the backward, we were able to get f prime of x is equal to I just need to write down the formula, f of x minus h minus f of x divided by h, and we got f double prime of x equal to f of x minus 2h minus 2 f of x minus h plus f of x divided by h squared. So this is what we got for the backward finite difference method. If you do the central finite difference method, you get f of x, f of prime of x, it's equal to f of x plus h minus f of x minus h divided by h, and f double prime of x is equal to f of x plus h minus 2 f of x plus f of x minus h divided by h squared. This is the central finite difference method, and this is central. So how we write down these formula in more generalized form? So what we do, that, as we said, you have a domain, right? Have your domain. You gotta apply the mesh or grid to your domain. So I'm gonna create the nodes I'm looking for. Now let's assume this is the node of interest here. Let's pick one here. That's the node of interest. We call that node I. Then the next one, and instead of using the x, we call I in that direction, we call y in that direction. J, and x is I. So y is called j, and x is called I. So this should be I plus 1. This node should be the I plus 2. So I is the node of interest. You want to develop the algebraic equation for that node I. So we rename everything to the right. It's x plus I plus 1, I plus 2. This is I minus 1, and this is I minus 2. These are the two nodes. If I go up, this will be actually j plus 1, because assuming this is I and j, right? So this is j plus 1, j plus 2. Sometimes I write it in the capital letter, sometimes a small letter, j minus 1, and this is actually j minus 2. So let's assume that you are interested in this node I. So if I'm applying, for example, the forward method, f prime at point I, the derivative at point I, right? That's partial f by partial x in the I at node I should equal to f of x minus h, right? Which is this one. So it's going to be f of I minus 1 minus f of I divided by this distance here is delta x, and this height here is delta y. So f I minus 1 minus f of I divided by the distance between the two nodes, which is delta x. Okay. If I would like to get partial f by partial y for node I, so I want to get the derivative in the y direction, it will be the backward point. So it's going to be f of j minus 1 minus f of I, or j. You can call that I and j, so it doesn't matter. But I'm unified that with I to be consistent. But you can call that I and j. This is I minus 1 and the same j. This is j minus 1 and I. This is I and j. Divided by the distance up, it's delta y. So this is the first derivative in the x direction. This is the first derivative in the y direction. Okay. What if I want to do the f double prime? Partial 2f by partial x squared. I'm still in the backward technique. So the equation said 2 point to the left minus 2, 1 point to the left minus the point itself. So I will do f of I minus 2 minus 2 f of I minus 1 plus f of I divided by h squared, which is delta x squared. Now, if I want to do partial 2f by partial y squared for node I need to go 2 points backwards. So it's going to be f of j minus 2 minus 2 f of j minus 1 plus f of I or j divided by delta y squared. So this is how to generalize the we call that the nodal equation for the backward finite difference. This is backward finite difference method. When you do the exercise to figure out the error for the compare the error order of the error for backward, forward, and central finite difference method, you should see that the error for the central finite difference method is better, it's less, right? And you can figure out the order of that error, but central finite difference method is give less error compared to the forward and the backward. And since now and coming, it's always better to use the central finite difference. So let's see how we can generalize the central finite difference approach for the first derivative and second derivative. Then we use that into a practical example to apply it. So again, I'm going to stick to the central finite difference method and develop a general format for that equation using I and J node to get that nodal equation. So again, here is my grid size here. So here is my target point. That's my point I. So this will be I plus 1. This will be I minus 1. This will be J plus 1. This will be J minus 1. Central mean that you take one point forward, 1 point backward. So I need 1 point to the right, 1 point to the left. So this is my x, y. So this is delta x here. Here is delta y. It's sometimes useful when you pick delta x and delta y are equal because it simplifies your algebraic equation. But in some cases, as we if you go back to the grid and mesh portion of that recording, you'll find that sometimes we don't actually have delta x and delta y are the same. If you have structured but not really uniform mesh, they will be different. So, and that's a problem, that limiting finite difference. Finite difference works fine when usually delta x and delta y are equal. If you start to change that, it's going to be complicated, but it doesn't work with non-structured mesh. It's only work with a structured mesh. Could be uniform or non-uniform, orthogonal all the time. They have to be orthogonal all the time. So the meshing has to be perpendicular. The grid lines has to be perpendicular. So let me explain that again here. So this is orthogonal, uniform, if you are picking these lines are perpendicular. This is structured, uniform, orthogonal one. I may end up having a problem with narrow mesh on that left side here. So your delta x and delta y are not equal. Still, finite difference method can apply. It becomes more complicated mathematically because terms will not cancel out, but still valid because they are orthogonal mesh. It's structured, non-uniform, but still orthogonal mesh. That's the beauty about finite difference method. Other than that, it doesn't work. So now let's go to the central finite difference method. We were able to list the f prime of x is f of x plus h minus f of x minus h divided by h, and the f double prime of x equal to f of x plus h minus 2 f of x plus f of x minus h divided by delta by h squared. I'm just writing down the plus. You have the error here, you have the error here. which we cut the equation at. But this is the central finite difference method. How we gonna generalize that? Partial f by partial x at point I will be the forward, the backward divided by h. So the first derivative will be f of I plus 1 minus f of I minus 1 divided by delta x. If you want to get the first derivative in the y direction for point I, will be f j plus 1 minus f of j minus 1 divided by, no, actually, this has to be 2, actually. I think for the derivative, because you are using the central, this is actually 2h. So I apologize for that. This has to be 2h, actually, and this is h squared. So this will be actually 2h in here. So this will be actually 2 delta x, and this will be 2 delta y. Just be sure of that correction here. That's how the central finite difference method apply. Now let's get the second derivative, partial 2f by partial x squared at node I is going to equal to f of I plus 1 minus 2f of I plus f of I minus 1 divided by delta x squared. And if you want to get the second derivative in the y direction at node I, it's equal f of j plus 1 minus 2f of I plus f of j minus 1 divided by delta y squared. So this is a general format of the first and second derivative in both x and y direction when you use the central finite difference method. Again, keep in mind, this finite difference method is very applicable for structured, doesn't have to be uniform or non-uniform, but it has to be orthogonal mesh. It's simply when you use quad element, that's where it's applied, okay? And again, you're gonna get the information at the nodal points here, okay? Let's jump into an example to see how we can actually apply that central finite difference method. This is what we're gonna stick all the time because of the improved error. So I'm gonna jump into an example and apply the central finite difference method for that. So let's assume that we have a bar that has a total length of 0.6 meter. And this bar is made of material that has a thermal conductivity of 10 watt per meter Kelvin. And I would like to get the temperature, find the temperature distribution along the bar if exposed to boundary conditions as follows. One face to the boundary condition shown. So one face here is kept at a temperature of 100 degrees C. The other face is kept at a temperature of 20 degrees C. So I would like to find the temperature distribution along the bar. To give you the sensation of the CFD approximation, I will solve that example first analytically. Then after we solve the analytical solution, we will do the approximation using the discretization method of finite difference, central finite difference, and get the answer for the same problem. So this example is just, I meant to show you the difference between analytical flow dynamics or analytical solution of a problem and the approximation, and how good or bad the approximation would be in a simple problem like this. So let's follow the basic steps when you apply any problem here. So number one, what's my design? My design is a solid bar of a total length equal 0.6. The thermal conductivity is given by 10 watt per meter Kelvin. I will set up my coordinate system x. So x is equal 0 here. X is equal 0.6 meters here. Okay. Again, I would like to have the units in between brackets instead of using parentheses to make things much easier. So that's my design. That's a setup of my problem. What should be the next step? Next step in the approach to solving a problem is to select your model. What's my model? Is the governing equation. What's your governing equation or equations, depending on the problem? Okay. This is a simple heat conduction problem. And if you go back and review your background about heat transfer, you will find that there is a very famous equation called the heat equation. And that heat equation is partial by partial x, k, partial t by partial x, right? Plus partial by partial y, k, partial t by partial y, plus partial by partial z, k, partial t by partial z, plus q dot is equal rho cp partial t by partial time t. This is what we call it, the heat equation. This is the general form of equation that control heat conduction in 3 dimensions, x, y, and z, Cartesian coordinate, with having a source of heat generation. This is a source of internal heat generation. This is simply 3-dimension conduction term, diffusion. So we have to get used to the new terminology here, conduction or diffusion, both are correct here, because later on when we start jumping into the finite volume technique, we will solve diffusion and convection problem, since we don't have anything that's in motion here, so the heat will move by diffusion or conduction into that bar. And the right-hand side of this equation is presenting the time effect. Okay, this is simply coming from the total energy stored into that bar. So whatever is going to conduct through that bar, maybe portion of that bar will store some of that energy. So this is the second step. This is my model. What's the third step? According to the chart or the diagram that we introduced before, you go back and look into that. Assumptions / simplification. Okay, that's your call. This is how accurate you want your results to be. So this is a very simple problem. I would like to solve that problem, and I may assume it's 1 dimension. So what my first assumption actually is to assume I'm going to solve this as 1 dimension problem. So this will be I'm going to solve 1 dimension. That's an approximation. If you do that approximation, actually, let's start with something more complicated. Number 1, let's do that assuming constant thermophysical property. I will keep that to the last just for a reason. So number 1, I will do constant thermophysical properties, which means that your thermal conductivity K is not function of X or Y and Z. We call that isotropic property, right? Thermal conductivity is the same in all directions. If that's true, K is not differentiable relative to X or Y or Z. I can take it actually outside the equation. So I will have K out here, K out here, K out here. So I will end up having the first derivative of the first derivatives of temperature. So I'm ending up having partial 2T by partial X squared. Second derivative of temperature relative to X, second temperature derivative relative to Y, and the second derivative of temperature relative to Z. And I should have K as a common factor between the 3 terms here. I will divide all these equation sides over K. I will end up having Q dot over K equal rho Cp divided by K partial T by partial time T. Rho is the density of that bar, Cv is the specific heat of that bar, and K the thermal conductivity of that bar. If you do that, you end up having this equation. This equation we call it actually Fourier bio equation. Sometimes it's called Fourier's equation for simplification, but this is the form of the equation. The second assumption I would go is actually assuming we have steady state. What do you mean steady state? Means that there is no change of time. I will wait long time enough until the temperature gets settled and nothing is changing, right? So if you do steady state, this means that any change relative to the time will equal to 0, which means that the right-hand side of this equation will be canceled, right? What is the opposite side of the steady state? What we call transient, which means that the time is counted for. But we are simplifying the problem here, so I'm going to solve for steady state. So this term will cancel out. I will end up having partial 2t by partial x squared plus partial 2t by partial y squared plus partial 2t by partial z squared plus q dot over k equal to 0. What equation this is called? We call the actual Poisson equation. Which constant thermophysical property, steady state, 3-dimension conduction with or without a heat source. This is called Poisson equation. Then the next simplification, I'm still under the title of assumption and simplification. Let's make that A and B so we don't mix up with the 1, 2, 3, 4. So the next simplification or assumption I would have is to assume that there is no internal heat source. So this is assumption C. No internal heat source. For those need to get the sensation what kind of heat source is, if you have a wire, electric wire going through that bar, and there is electric current going into that wire, you know that electricity will be transformed into a kind of a heat source. So there will be internal source of generating heat. If you have a chemical reaction, if this is a concrete container and you have some chemical material that's interacting to each other or leading to a chemical reaction that exothermic reaction that produce energy, that's a kind of heat source. If inside that bar there is a nuclear fuel that exposed to a fission reaction, it will generate heat. This is all called the internal source of thermal energy or heat generation. This is just an example. What do you mean by what I meant by the internal source of heat generation? So we will assume this problem doesn't have any kind of heat generation source, which means that the term Q dot will equal to 0. So the Poisson equation will end up having that format: partial 2t by partial x squared plus partial 2t by partial y squared plus partial 2t by partial y squared, z squared is equal to 0. And this equation, we call that Laplace equation. The last and final assumption, this is what I kept from the beginning, is to do one-dimension problem. If you do one-dimension problem, it's going to be partial 2t by partial x squared equals 0. It's still a Laplace equation, but it's only for one dimension. So again, this is my solid bar. This is the x direction. X is equal 0 here. X is equal 0.6 meter here. Thermal conductivity is given by 10 watt per meter Kelvin, right? And I would like to get the temperature distribution here. So the next step is actually to solve. That's step number 4, is to solve. Now you have multiple options. You solve analytically, you solve experimentally, and you solve numerically by approximation, right? So I will do the analytical solution first to get the sensation when we solve numerically, how accurate the numerical approximation is compared to the analytical solution. Again, remember, analytical solution, you will end up having an equation, a formula that's continuous over that domain from x equals 0 to x equals 0.6. Then you can use the equation to substitute by any coordinate between 0 and 0.6. You get the temperature. There is no restriction on the grid or grid boundaries or anything like that. You will get all the information at any location. If you want to get the temperature every 0.0001 meter along that bar, you will be able to do that because of the continuity of the function, or having that continuous function. So let's try to solve analytically. Before we solve, we have to set up a boundary condition. The boundary condition was given that phase is at 100 degrees C. This phase is at 20 degrees C. So I can reformat the boundary condition as x equals 0. The temperature at that location is given by 100 degrees C. At x equal L, which is equal 0.6 meter, the temperature at x equal 0.6 or L is given by 20 degrees C. And it's obvious here, this is a Dirichlet boundary condition that has a fixed value at both sides of the boundary. So I will take that equation and I would like to solve that analytically. So I'm going to solve analytical solution. Okay, differential equation, second order homogeneous differential equation. Second order homogeneous differential equation. It seems to be very separable, right? So I can easily, I can simply do the integration, right? If I want to get the temperature as a function of x, and I have a second derivative of the temperature, I would simply integrate the equation. So I'm going to go and do integration for the second derivative. I will integrate both sides, right? And the integration should be done from the beginning to the end. So if you want to do the integration, you integrate the second derivative. I will get the first derivative. You integrate 0, it should give you constant. I'm called that C1. I'm going to go ahead and integrate both sides again. So if you integrate the first derivative, you'll get the function itself. And if I integrate C1, it's going to be C1 times x plus another constant C2. So this is a general equation, and it seems to be linear, right? Constant times x plus constant. So that telling me that temperature distribution has to be linear within that boundary. So if I'm plotting T as a function of x versus x, and this is the ending boundary here, I should start at 100 degree, then at 20 degree, which is the ending point here, I should simply get a linear change in the temperature along that bar. This is what this equation is telling me. So what I need to do right now is just finding the coefficient C1 and C2. How you get the two coefficients? You have to apply the boundary conditions. Two unknown, I need two equations, I need two boundary conditions. So let's stick to the equation and start actually applying the boundary condition. The first boundary condition is at x equals 0, your temperature is 100 degrees. And I have x equals 0, I have a temperature of 100 degrees. So 100 degrees equals C1 times 0 plus C2. And this equation is magic. It gives me C2 equal 100. Now, second boundary condition, at x equal 0.6 or L, the temperature is 20. So 20, I should have C1 times L plus C2 is 100. I simply can get C1 out of this. 100, it will go to the other side with a negative value. So it's going to be minus 80 divided by L, which is going to be minus 80 divided by 0.6. Right? Now I can get the actual equation, T as a function of x is equal to minus 80 over 0.6 times x plus 100. Then if you divide that, it's going to be minus 133.3x plus 100. It's obvious. This line has a negative slope. It's clear. Temperature decrease as you go further with x. So at x equals 0, if you put x equals 0, I end up having T at x equals 0 is 100. So it satisfied the first boundary condition. If I put x equal 0.6, okay, which is here 0.6, can I cancel out? I'm going to have minus 80 plus 100. It's going to give me 20. So by applying this boundary condition, this formula seems to be perfect and correct. Now, if I want to get the temperature at any location between 0 and 6, this equation is valid from x is greater than or equal 0 and x is less than or equal 0.6 meter. Now, this is a continuous function over the domain from 0 to 0.6. If you want to get the temperature at distance of 0.1 nanometer, You got to just substitute with X, you get the temperature distribution. But we know if I have 2 points, I can simply connect the 2 points to get the linear relationship, then I can get the temperature at any location. This is the analytical solution so far. Our next step is to start using an approximation method. We will focus on the finite difference method. I will pick the central finite difference method, then I will apply that numerical approach or scheme to approximate the differential equation. So I'm not gonna do the integration. I'm gonna stick to this equation, and I will approximate that equation using the discretization finite difference method technique to end up with a series or a set of linear equation, algebraic equation to solve numerically. Then we can get the solution. Then we can actually compare what we get analytically with what we get approximately using the finite difference method and see the accuracy of it.